So I thought I'd start today by just thinking about what we've been doing so far. And it's all really been about formulae. And I did say to have a formula sheet that you gradually build up, so that's sort of been lodged in your brain, possibly some of that now, because all the problems seem to revolve around the same sorts of formulae. So I thought we'd start today by just writing down on here any formulae we remember that might be relevant to an engineering problem. Who would like to start the ball rolling? Force is mass times acceleration, like that one. Stress is force over area. A formula that's quite relevant at the moment with your assignment, is it not? Somebody had their hand up over there somewhere, Marcus? Right. Another one. Density is mass over volume. Note the symbol for density. How do I say that? Rho. Weight is mass times gravity. Sort of related to that. Weight is a force, equals mass, and gravity is the acceleration due to gravity. So that's an acceleration, the gravitational pull towards the centre of the Earth. So same formula, really. Yep, good. Any others? L0 for original length, yep. Some more basic formulae, Marcus. Is this one of those situations where you start a sentence and wish you'd never started it? Precious. Yeah, you're right so far. Force over. No, force per unit area, yeah. Force over area. The effect of a force spread over an area. Good, yeah. Area of a circle. Yeah. Circumference 2 pi r. So they're related particularly to a circle, aren't they? Volume of a cylinder. Pi r squared L. Good. Area of the base times the height or the length. Yeah, so pi r squared times the length. Well, that's a good selection, isn't it? Look at those. Do you know all them? So now you're in a engineering scenario, and you're going to have to do a quick calculation. I'd like you to try and do this without a calculator. You're caught on the hop, you know, you're in the engineering workshop, and there's a piece of steel tubing. It's hollow steel tubing, and you've measured the outside diameter to be 1.9 let's make it a little bit bigger, 190 millimeters. That's the outer diameter, and the inner diameter to be 150 millimeters. I'm thinking now that I want to do this without a calculator. So you can do this rounding, okay? The length you measure to be about 1.5 meters. And the density of steel 7.9 grams per centimetre cubed. Which is 7,900 kilograms per metre cubed. And somebody said to you, what's the weight of that thing? Because will this device I've got, this lifting apparatus, lift that? Or is it safe enough for a person to lift? So I want to know what the weight of that is. So without a calculator, without referring to any formula sheet, remembering the formula that are involved, see if you can just work out what the weight of that is. Estimate it. What sort of roundings would you do? It's usual, if you're estimating, to do it to one significant figure. This torsion equation, torsion in shafts, what we're going to do is use a formula, very like the bending equation, to measure how much twist there is in a shaft, or what torque is required to twist the shaft, things like that. And as with the bending equation, there are certain assumptions we make, and they're outlined here on the beginning of your handout. So we assume, when we're going to use this torsion equation, that radial lines remain straight after twisting. So that means we're not bending the thing beyond Young's modulus effectively, or its yield point. As if I were to let go, it would go back to its original plate again. Circular cross sections remain plain, i.e. there's no distortion, so no necking, anything like that. In other words, we're not putting enormous strains on this. We're laying well within the safety limits. The twist per unit length is constant, so I'm not twisting more at the ends as I am in the middle. It's nice and uniform right across the shaft. The materials remain elastic. We're not going beyond the elastic limit. The shaft diameter is uniform, so we're not talking about a shaft that's getting bigger as we go along or narrower. And the bending is negligible, so we're only considering twisting it, not bending it as well. So with those assumptions in mind, we have this thing called the torsion equation rather, which is here. The torsion equation. Note how similar it looks to the bending equation. We've got T over J equals tau over R equals G theta over L. That's a new symbol, tau. Looks like a sort of a reflected J, or a T with a little hook on the end, if you like. T represents the applied torque, which is the angular equivalent of moment, really. J is the J-polar second moment of area, as we would call it, as we'll discuss that in a minute, but it's to do with the properties of the material, whether it's a circular shaft, whether it's hollow. A bit like the second moment of area for bending, it's to do with the makeup of the material. Is it an I-beam? Is it square section? So we'll talk more about that in a minute. Tau is the shear stress induced, trying to twist it, that stress that's being induced. R is the radius. G is the shear modulus, that's very like Young's modulus, but applied in a shear effect rather than a bending effect. Theta is the angle of twist, so if I do manage to twist the shaft, that's how much it's been twisted by, measured in radians, and L is the length of the shaft. So those are the values that go into this torsion equation. Now if we compare it with the bending equation, you can see that they're sort of similar idea. And just like the bending equation, we only ever use two of the ratios. So depending on what I'm given, I might use that ratio and that ratio, in which case I don't use that. A bit like the sine rule. We only ever use two of the ratios. And if we've got the two that we're interested in, say these two, then it's a case of just rearranging that little formula to find out, say, what T is or what tau is, putting the values in, checking the right units, and so on. Exactly the same as we do for all the other formula that we use. Just another formula to add to our toolbox, that's all it is. So this second moment of area, like the one for the bending equation, we can derive what these are for particular shafts. It's to do with working out how much effect each little element of this thing. So if we can consider each little particle inside here, and this thing's been trying to twist around this central axis here, then what's the effect on that bit of the mass, what's the effect on that bit of the mass, and so on. So we find the overall effect by integrating over the whole distance from there to there. Use calculus, in other words, more on that later. But luckily for us, for some common shapes like this solid cylinder and a hollow cylinder, the answer comes out to be something that we can use. It turns out to just equal pi d to the 4 over 32 for a solid shaft. And if you remember back to the second moment of area for the bending equation, this is similar. You're just taking away the inside bit, which is what you were talking about earlier. You just subtract the middle bit. So it's the same formula, but just taking away the middle. Yeah, capital D to the power 4 minus small case d to the power 4. Yeah. Outer and inner diameters. So we might be given J, the polar second moment of area. We might be given T, the applied torque. We might be given the stress. We might be given shear modulus. We might need to work out what the angle of twist is. Depending on the problem we've got, we need to work out, well, which ratio am I going to use? Am I told these things, or do I need to work out what they are? Plug them into the formula. Are the units correct? Rather than plug them into the formula, and out comes the answer. So let's have a look at some examples of how these things are used. Two other formulae to add to your formula list that will help in this situation. The power is related to the torque in a rotating shaft that's been put on this twist. So this is now a rotating shaft with angular velocity omega. So that's the angular velocity of the shaft. So if I were to look at a cross-section of the shaft here, say it was a solid one, it would be rotating with angular velocity omega, measured in radians per second. I'm applying a torque T to this shaft, making it rotate, and the power output of the shaft is given by the torque multiplied by the angular velocity. So I can use that formula. If I'm, say, told what the angular velocity is, and I know what the power is, I could work out the torque, because I might need that in the torsion equation. A reminder of a formula that we've come across that relates the angular velocity to the frequency, omega equals 2 pi f. So that's another formula to add to our formula sheet. I'll be tempted to put all these together, the torsion equation, this equation, and this equation all together, as well as the equations for the polar second moment of area. Yeah. So we might also add the formula V equals omega r that relates the linear velocity v to the angular velocity omega. So look, quite a few formulae to use. It's all about now, as we did in a few minutes ago, identifying the right formula, getting the values in the right units, plugging them into the formula, and out comes the answer. Same procedure.